Welcome to lesson 33. So we're going to talk about using z-methods or z-procedures for estimating a proportion. So specifically, we're going to be making a confidence interval for a proportion from a population. And then we're going to go ahead and we are going to focus again on calculating that minimum sample size required in order to make a confidence interval of a certain confidence level no wider than a certain amount. So confidence interval for P. So we're going to want to use this when we want to estimate the proportion of a population. And we're only going to look at one population in this class. And so we're going to have our conditions. So we're going to want to know that we have, and pretty much, this is always going to be true. We want to have our sample be representative of the population that the sample came from. If not, we're going to have to write an asterisk and say, hey, maybe this doesn't apply to everyone. And then here is where things change up, because remember before we had to say, oh, the sample size has to be big enough. Well, it's changed a little bit. So we are looking at what's called binary data. So we have a categorical variable and we've broken it up into two categories. So once you do that, you need to know that you have at least 10 successes that you observed and at least 10 failures that you observed. And so you can go ahead and plug them into here and make sure that they're at least 10. Or you can even just look at what was observed. What did I observe at least 10 in each category? And if so, you should be okay to calculate a confidence interval. So from there, it's going to be p hat. So our point estimate is going to be the sample proportion, plus or minus. So because we're using z methods again, you can use z star, which is great. So that 1.645, 1.96, those numbers, you can use them again. And then times a standard error for p hat, which is this part here. So notice that for the confidence interval, the standard error here for p hat, for a confidence interval, it's this square root and it's p hat minus times 1 minus p hat over n, square root that whole thing. I am pointing this out because the standard error for p hat when we do a hypothesis test is slightly different. So just keep an eye on that. And then just a reminder, so this is z star back from our z table. And what's really cool is if you have that t table that I gave y'all, the z star critical values, they actually are at the very bottom of that t table. For those of you, who don't want to memorize these numbers, I have, but I've used them a very long time. So returning to our question, when I focused and asked people, hey, if you had to have extreme weather, so weather that's too hot or too cold, which would you prefer? Would you prefer too hot or too cold? So I went ahead, I asked the ST201 class this term, and 191 folks responded, and 145 of them said they would prefer weather that's too cold. And we had about, 46 individuals say that they would prefer too hot. So now we want to say, let's calculate a 90% confidence interval for the proportion of all Oregon State University students that prefer weather that is too cold over too hot. So starting off, what is my question of interest? Knowing that I want a confidence interval, it should start with a what is. It should be an open-ended question. So, what proportion of all OSU students prefer weather that is too cold? And I like to insert the versus weather that's too hot, just so I know what I'm comparing to. And if you have this worded just right, in our next problem, I can pretty much just yank this part out here. The proportion of all OSU students that prefer weather that is too cold. That'll be my parameter of interest. So my parameter of interest, notation-wise, it gets the letter P. That is the letter we use to represent the population proportion. And so it's going to be the proportion, so there's the type of parameter, of all OSU students. So this is my population. And then that prefer, I should probably write the word that prefer whether that is too cold. That is my variable of interest. That's the category that we're calling a success here. And so then for inventory, you might even go, okay, well, X, that's just the number of successes. My count is 145. My sample size is 191. And my p hat, that's 145 over 191. And I rounded this, at least here, although when I made the calculations, I left it as 145 over 191. But about 0.759. So that will be my inventory for now. And I will be able to write out a z-star, although I have that in another step. So my confidence interval here, or my confidence level, so they wanted 90% confidence, so I'm just going to write 90% confidence. That means my z-star critical value should be equal to, and you can use that table. I happen to have them memorized, at least those particular three. 1.645. That's the z-star critical value that goes with the 90% confidence interval, at least when you're using z-methods. So then we need to check our conditions. So did we take a random representative sample here? Can I say, hey, these students definitely represent all OSU students? Ideally, yes, but I did not, right? I took absolutely a convenience sample. I had a number of ST201 students right there, and that's who I surveyed. So, no, so watch out. The results may not apply to all OSU students. So we're still going to write everything up in terms of that population, but it's worth an asterisk at the end saying it may not actually apply to all OSU students. Then based on the central limit theorem, do we know that the sample size is going to be big enough? That's going to be approximately normal. So remember, we're not going to use, hey, is 30 big enough anymore? We only want to know, hey, is the sample size of 30 big enough? That only works if we're using a quantitative variable. So now, if I go ahead and plug into this, I have 191 folks times my p hat, so that's what, 145 over 191. That's just going to be 145. It's just going to give me the number of successes that I started off with. And that's definitely at least 10. 145 individuals preferred too cold. That's definitely more than 10. And honestly, I know right off the bat, if I had 46 failures or people who preferred hot weather, not that they're failures, but that's definitely over 10 as well. But just to show you, so 191 times 1 minus 145 minus 191, you plug it in, you will get 46, or you should anyway, and that is at least 10 as well. So for confidence intervals, this one's super easy because you may not actually have to calculate n times p hat, because you can just say, oh, there are this many successes. And then as for the second one, you could say, okay, well, there are this many successes and there are this many failures. And as long as they're both 10, you're good. So looking here, I would say definitely we have a big enough sample size here. I would worry, though, about this sample being random and therefore representative of the population, because absolutely it was a convenient sample. So then here, if I want to go ahead and calculate the confidence interval itself, I'm going to go ahead and just plug in, so 0.759 out of 191, a z-star of 1.645. So I have everything I need to plug in here, which I know it looks like a little bit less, but it's because of this part right here. It just uses p hat and n. So my point estimate where I'm going to start is the proportion we saw in the sample, plus or minus 1.645 is my critical value, times square root 0.759, 1 minus that, which is going to be about 241 all over 191. Plug that in, and then I'm going to get 1.759 plus or minus. I'm going to do steps here. 0.051. I'm just going to round out to 3 places. And I'm going to get my confidence interval in interval notation. It's going to be, okay, then my confidence interval in interval notation is going to be about 0.708 to 0.810. So roughly 70.8% to about 81%. And no units. So anytime we're dealing with proportions, they do not have units. So don't include units here. So almost all the way through, now we have to go ahead and do that write-up where we write our 2-part conclusion. Okay, so now we want to go ahead and do our write-up for our confidence interval. So I'm just going to write it again so I can remember exactly what it is here. So it's a 90% confidence interval. And do note it's set up a tiny bit differently. So the 90% confidence interval for it's going to be proportion instead of mean. So the proportion of this should be your population right here. So all OSU students and this is my category of interest. So I was focused on folks that prefer too cold. So prefer too cold weather. So the proportion of all OSU students that prefer too cold weather is estimated to be between 0.708 and 0.810 with a point estimate of, so this is the p hat from my sample. So that 0.759. And p hat should always be smack in the middle of these two, like exactly in the middle. Like I could average the 2 endpoints and I'll get back to the middle there. So keep in mind it's set up a little bit different, but it's still very similar. We're going to want to see the confidence level. We're going to want to see the word proportion in there. We're going to want to see a population. And we're going to want to see the category of interest. And then we want the interval with the point estimate. Just be cautious, there are no units here. And then like I said, I might say may not apply to all OSU students. Because we left a lot of folks out, right? There are a lot of folks that are not represented whatsoever. Grad students, for instance, are not as likely to be in ST201, that kind of thing. So may not apply to all OSU students. So it's a disclaimer. So then, kind of a throwback, we did this back when we did confidence interval for Z method. So I want to say week 6 or so. So suppose you want to make a certain level confidence interval, but you want to make sure that your interval is no wider than a certain amount. So you need to designate like what the smallest or what the desired margin of error is. So this should be half the length of the entire interval. And you can use this here. So this will be the sample, like the smallest sample size you need in order to have a whatever confidence level interval such that that is not going to be wider than that specification. The big thing that's different here are these P stars, right? So P star is going to be your best guess for P. So if you have sample information, you want to use P hat. If you know nothing, you're going to use P star is equal to 0.5. So that's just the most conservative guess you could possibly use. However, if you have sample information, use the sample information. It'll be probably more accurate. Not to mention, using 0.5 will give you the biggest sample size versus any other value of P star. So back to that question where we said, hey, would you prefer too hot or too cold? Suppose the Beaver store is really interested in this, and quite honestly, a marketing team really would be. So suppose they want to estimate the proportion of all OSU students that prefer too cold of weather. Maybe they'll order more parkas or something, or gloves. So suppose they want the margin of error no larger than 0.02. So that means that I have my P hat, and I'm not bigger than 0.02 in either direction. That means the entire width is no wider than 0.04, like the whole interval. So 0.02. And suppose we want a 90% confidence interval. So that tells me to use a z-star of 1.645. What is the smallest sample size I'll need? So n, I don't know. We'll figure this out here. Then we need to figure out what we're doing for P star. So because I already took a sample and we have sample information, we should use P hat. We have a P hat to use, so let's use that 0.759 that we got from our sample earlier. Okay, so I'm going to focus on this part right here, this right-hand side. So I'm going to go ahead and I'm going to take my 1.645 divided by 0.02, square that, times this 0.759 times 1 minus that. So it's, I think, 0.241. So do this math right here, it comes out to 1,236.89. So just to draw everything back together, my sample size needs to be greater than or equal to 1,236.89. So remember, like, when you go out, and since these are people, you can't sample 0.89 people. So you have to think about rounding here. In fact, we're always going to round up, because if you think about it, if I need a sample size of at least this much, 1,236 won't be quite enough. So always round up in this case. Anytime you're doing a sample size calculation, always round up. So we're going to sample, or you should sample at least 1,237 students in order to make sure that your 90% confidence interval is no wider than 0.04. That's what that's coming out to. So that's it for lesson 34, and we're going to talk about hypothesis tests next.